Alright, so I'm going to run through an example of Dijkstra's algorithm at work on a 10-node graph. So here is our example graph. These yellow balls are our nodes. It's a bi-directional graph, so the arrows represent the directions, with these numbers in yellow representing the weights. The numbers inside the balls are just the label of the vertex or the node. I might use those words interchangeably. And here we have a table of the distance labels for each vertex. Initially they're all set to infinity as per the algorithm, and these nodes will change colour to orange and blue when the shortest path is being computed or when they've been reached. So first we start at node 1, vertex 1, and this is updated to be 0. Next we go to the two outgoing edges, just 6 and 2, and we update these values, 10 and 3. And then we choose the minimum of these two, because that will be the shortest path, and it's vertex 2, so we move to vertex 2. And here we look at all 4 outgoing nodes. Again, we update all 4. Just say, for example, to get to node or vertex 7, we have to go through 2. So we're going this way and then this way. So it's going to be 3 plus 7. You can see here, it's exactly that. Sorry for the noise. Background, there's some construction going on. And so we add all of these into our distance label table. And again, we find the smallest of the 4, which is to 8. Again, we look at outgoing edge of 8, to 3, to 2, to 5. And here, 5 has 3 outgoing edges, 1 to itself, 1 to 10, and 1 to 8. But we've already been to 8 before. We knew that here, to get to 8, it was 3 plus 1. So we have a look. This new distance to 8, the new path to 8, is 3 plus 1 plus 10 plus 2, which is clearly not smaller than what we've already got stored, so we don't update it. And we move on, we've got a 10, we've got a 4, first one, and now here is our first updating of the table. So 4 takes us to 6, and we've already been to 6. Here, to get to 6, was 10. It was a short, it's one edge, but the weight is 10. Now our path to 6 this way, all the way around, we're going by a 4. And 4, we can see back here, 4 is 3 plus 5, which is 8 to get to here, and then to get to 6 from 4 is only 1. So our new path is actually 3 plus 5 plus 1 is 9. And since it was 10, 9 is shorter than 10, so we update it here. We can see our new distance is 9. So now we've gone to 6, we go back to 4. At this point it might look like we can't get anywhere because we're currently pointing towards only 4, but 7 was put back in our queue way back when we looked at 2. So we will now look at 7, and 7 points to 6, and this doesn't improve because this new path to get to 6 is 3 plus 7 plus 2, which is 12, and that's not less than what we already have over here, which is 9, so we don't update it. 9, however, we can't ever reach. It doesn't have any edges pointing to it, so it's just left as infinity. And that's the end of the algorithm.